Greetings to you all. I trust this video meets you in safe hands. In our last video, we looked at the topic work, energy, and power, and we concentrated on work and energy. In today's video, we will be concentrating on power and also conservation of mechanical energy. I would just advise that as we watch this video, we should pause the video intermittently so that we'll be able to jot some very important point down. In today's video, we'll also be looking at a very brand new topic, application of mechanical energy, that is simple machine. Sit back and watch attentively. God bless you. So looking at the topic, power physics. So looking at the topic, power and conservation of mechanical So our topic, power and conservation of mechanical energy. Without wasting of time, we go straight to the point. What is power? Power is simply defined in physics as the rate at which work is done. In other words, power is defined as the time rate of doing work. It is defined mathematically as P is equal to work done over time. So let's call this our equation number 1. From equation number 1, P represents power and is measured in the SI unit of watts. W represents work and is measured in the SI unit of joules. And then T is the time taken and is measured in the unit of what? Seconds. Recall that work done is equal to force times distance. That is linear work done. We also have it as work done is equal to MA times height. And so substituting these variables into this equation, we're going to be having 3 different equations of power. So we say power is equal to force times distance over time. We call this our equation number 2. Also, power is equal to mg. There is mg, so we say mg times height all over t. We call this our equation number 3. Now, we want to distinguish between energy and power. Suppose there are two students that have the same amount of energy and they are given the same task to do. Let's suppose they are given 10 books each to take to the library of the school. And then, who is that student that has a greater power? The student that finished packing the book first, or the student that finished packing the book? In a more faster rate, we consider that student as having the greater power over the other student. So they will have the same energy, but the other one has greater power. The one that finishes packing the book within a short period of time is said to have the greater power. Do you understand? So at this point, we will be looking at some little examples that has to do with these equations. Let's look at our textbook I am using this new school physics. If you have it, we'll open to page number new school physics, page 37, exercise 3. A man of mass. A man of mass. Example number 1, new school physics. A man you pause, right?
Yeah.
Is 10 meters a second. Calculate the power. Solution. As usual, let's read. A man of mass 550 kilograms ascends a flight of stairs 5 meters high in 5 seconds. If the acceleration due to gravity is 10 meters per second, calculate the power. Solution. So collect the variables involved in the problem, that is our data collection. So our data, we have mass. M is equals to 50 kilogram, and what time t is equals to 5 seconds, and the acceleration due to gravity is 10 meters per second squared. Now, which equation do we go with? Of course, oh, we forgot something, the height. The height h is also 5 meters. So we go with equation number 3. And so we state using power is equals to mg times h all over t. We substitute the variables, and so we have our mass is equals to, our mass is 50 times 10 times height is 5 all over what? All over 5. So we go 50 times 10 times 5. We have 2,500 by 5. And so say therefore our power is equals to 500 watts. Simple.
You understand?
Right about now, we'll be looking at a subtopic, conservation of mechanical energy. Mechanical energy. Conservation of mechanical energy. Conservation of mechanical energy takes its roots from the laws of conservation of energy. Recall in your JSS classes, we state the law of conservation of energy, which states energy can neither be created nor destroyed, but can be transformed from one form to another. And so in this subtopic, we shall be looking at conservation of mechanical energy and how the law is applied here. Recall that anytime we are discussing mechanical energy, we are discussing two forms of energy, namely potential energy and kinetic energy. I won't draw you a lot of theories, but I just analogize something here to explain to you what it means by conservation of mechanical energy. Now look at this meter rule. We define mechanical potential energy as the energy possessed by a body by virtue of its position above the ground level. And so at this point, the knife edge you see in my hand is attaining potential energy at this level. because the height from here to the book. At this point, it is all potential energy. Kinetic energy is zero because the knife edge is motionless. If I drag it down to this point, at this point we are having both potential energy and kinetic energy. Kinetic energy because the knife edge has moved from this point to this point. Potential energy because the knife edge is from here to here and this is the height. And if we bring it down to this point, you only have all kinetic energy and potential energy zero. So the simple equation that describes what I just analogized here is simply P E is equals to K E. So let's state the law of conservation of mechanical energy. The law of conservation of mechanical energy states, in a closed or isolated system, the total mechanical energy remains constant or conserved. That is the meaning of this equation. By substituting in the variables we have, mgh is equals to half mv squared. You call this your equation number 4. We shall be looking at example number 2 to how we're going to use this equation. So we have example number 2. Still with your new school physics page 37, we're looking at question number 9. We write, at
Okay.
moving with a velocity of 10 meters per second. So let's read. Example number 2. At what height above the ground must a body of mass 10 kg be situated in order to have potential energy equal in value to kinetic energy possessed by another body of mass 10 kg moving with a velocity of 10 meters per second? Simple. Solution. As usual, data. Let's say mass 1 m1 is equals to 10 kg. And another body possessing kinetic energy is having mass, let's say m2, is also equals to 10 kg. And then our velocity v is giving us 10 meters per second. Mind you, g is equals to 10 meters per second squared. So using the equation, this, you have mg h is equals to half mv squared. So this is congruent to m1 gh is equals to half m2v squared. So we substitute in the variables, and so we'll have 10g. Yes, let's put 10g times h is equals to half 10v squared. This go and this go, since we have 10 on both sides. So let's do the second substitution. So we have 10 times h. Because the question is at what height? So we say 10 times h is equals to half squared should be 100. So we have 100 over 2. You see that? So we have 10h is equals to 1 over 2, that's 50. And so you divide both sides by 10. And so your 10h over 10 is equals to 50 all over 10. This go, this go, this go, this go, and so therefore the height in question is 5 meters. Very simple. And so I will advise you to make use of this and also this to solve some questions that are related. At this point, I will be giving you some class work to do at home.
Yeah.
So I've changed my mind from class work to assignments. I'll simply pick up your new school physics and help me solve this. Please don't fail me. New school physics, page 37, question number 3, 6, 8, 11, 12, and 13. They are very simple. I want you to help me solve those questions correctly and get back to me. God bless you.